Okay. Sorry about that. Okay. So what's important to remember with linear algebra is that we're going to be setting everything up in matrices, and so matrix algebra will be used. So for example, if you have three matrices, A, B, and C, and you multiply them, A and B, by each other, this is what it looks like. So let's say A is a 3 by 2 that looks like this. So the dimensions are 3 by 2. If you multiply that by a B, which is a 2 by 2, 5, 9, 7, 2, for example, the first rule for matrix algebra is the inner dimensions need to agree. So this has to be the same as this in order for that to be multiplied. So the 2 and the 2 have to match. And then the resulting C that comes out of the multiplication is going to be the outer dimensions, 3 by 2. So the way matrix algebra works is you take the first row and you multiply it by the first column. And so you do 3 times 5 plus 1 times 7. So 3 times 5 is 15, 1 times 7 is 7, so that's going to be 22. And then to get the next element of the 3 by 2, I'll build this so you can see what it looks like. You're going to take this row and multiply this column. So it's 3 times 9, which is 27, plus 1 times 2, which is 2, so that's 29. Then you're going to take the second row and multiply it by the first column. So that's going to be 8 times 5 plus 6 times 7. So that's 82. So you keep doing that, and that's how you fill in all the elements. And I'll show how you can rewrite the equations to basically make use of this, but this is how matrix algebra works. So in MATLAB, if I set up my A matrix, you would just make sure that you build it the right size. It's really important for matrix algebra that these are the proper size. So my A is a 3 by 2, and my B is a 2 by 2. And then if you do A times B, you get what we just calculated. So it's just doing those operations that we just went through. So there's a couple important pieces of matrix algebra that you need to know. The first thing is that you don't divide matrices, you invert matrices. So everyone is, it's really unclear to me how much this is review, but if you have a square matrix, like B is a square matrix, there is something called the identity matrix, and if you multiply B by the inverse of B, you get the identity. So the identity is just 1, 0, 0, 1. And so that's how you actually do division, and so I'll show you that in a second when we actually solve an equation. But in MATLAB, if you want to invert a matrix, the function is inv, and that inverts it. And so that way, if you want to do matrix algebra, you don't divide by B, you multiply both sides by the inverse. And I'll show you that in a second. So let me just have that down, that's what the inverse is inverse B. So let's talk about how we're going to use this for solving a system of equations. So we're going to convert a system of equations into matrix form. So for example, the example I'm going to use is 3 equations, 3 unknowns, and I'm going to use x1, x2, and x3 as my 3 unknowns. So let's say I have this equation, 3x1 plus 2x2 plus x3 equals 2. So that's my first equation. My second equation is 5 times x2 plus 2 times x3 equals 1. And my last equation is x1 plus 3x3 equals 3. So this is a 3 by 3 system. And so if you want to write this in matrix form, you're going to pull out all of the coefficients in front of all the unknowns into your first matrix. So 3, 2, 1 are the coefficients of the first equation. 0, 5, 2 are the coefficients of the second equation. And then 1, 0, 3 are the coefficients of the last equation. And we call, this is consistent in linear algebra, this matrix is called capital A. That's why we use the lowercase a as the coefficients. That is going to be multiplied by a vector of the unknowns, x1, x2, x3. So remember, that's something that you don't know. And we call that vector x with the bar. In textbooks, they'll often bold the A or put 2 lines over the A to indicate it's a matrix. But I'm just going to write A. And then the right-hand side values are in an array called B. So what's nice about this is this reduces your writing quite a bit. You can just write that whole system as AX equals B. And we're going to write a lot of algorithms for those 3 different algorithms that I just explained. We're going to write those. And so I'd like you to have in your notes how to write this out. This is for a specific set of 3 equations, 3 unknowns, but let's write it out in general too. So let's write it for just any coefficients, any B value, but just for 3 equations and 3 unknowns. If you write much more than 3 equations and 3 unknowns, it's just too much writing. But we're going to write it for 3, and you can generalize it for n in your code. And when I write the algorithms, I'm going to be referring back to this general form of the equations, but you could think of it as a specific example if that makes it easier for you to think about. So it's the same thing. You're going to just have this broken up into this matrix, and the coefficients are numbered this way because this is the way that you number the elements in the matrix. That's purposeful. And so the way, when you set up the matrix, it will kind of make sense. So that's how you would break down the matrix in general. So we're going to solve this 3 ways. The first way is the easiest way, which is using the inverting function in MATLAB. Sorry, I should say inverting matrix method. The second way is called an iterative method. And this is the easiest one to program, but people think it's insane, but this is actually how most modeling codes solve systems of equations. And then the last way is called an elimination method. And the last 2 are what you're going to program. The first one is using the intrinsic functions, basically, in MATLAB. So let's just talk about inverting the matrix. Okay, so this is the easiest method, but it is the most expensive. It's basically not possible to do this for any real system or real application. So as long as you have like, a couple hundred unknowns, this is a fine method. But once you start getting into millions of unknowns, which is what most engineering problems are, you can't use this method anymore. So the way it works is you have your system of equations, ax equals b, and then you're going to use matrix algebra to solve this equation. So like I said, you're going to multiply both sides by A inverse. And that's the same, like equivalent to dividing both sides by A in regular algebra. That's going to leave you with the identity when you multiply A inverse by A on the left-hand side. And the identity is just like 1 in algebra. It just basically is like multiplying by 1. So you can take it out, and this is how you solve for x, your set of unknowns. So there's a couple different ways to do this in MATLAB. So the first way is using the inverse operator. So you'll set up your A matrix and your B vector, and you'll just invert it. So if I set these two matrices up, here's my A, a 3 by 3, and my B is going to be 2, 1, and 3. So if you want to solve, you just do I and V of A times X, times B. And that will solve for all your unknowns. So that's the quickest way to do it when you have a small number of equations and unknowns. But actually, if you do that in the M file, it will tell you not to. And what it wants you to do instead is use the backslash operator, A backslash B, because A backslash B does the inverse, but it uses a more sophisticated elimination method that reduces some of the computation cost. So for big problems, this eliminates like 1/3 of the computations, which is significant for some. And then there's also another function called linsolve. And linsolve is a function that you give A and B to, and it will output X to. They're all doing something very different. This one uses LU decomposition, which is an elimination method. This one is doing Gauss elimination, which is the same thing you're going to be programming in the lab. And this one is going to be doing, this is just inverting. So these are about the same cost, but this one is more expensive. Any questions about that? Okay, so let's talk about an iterative method. So that one's pretty easy to set up, very little programming, but very limiting in its applicability beyond kind of classroom settings. So what we're going to look at is how to program something called Gauss-Seidel, which is an iterative method. So what it does is it basically just guesses and checks until it's right. And it's honestly how all modeling code work, because a lot of times the system, you already know pretty close what the answer should be, but it's only changing a little bit from time to time. And so these iterative methods are actually really useful in engineering problems. So what you do is you take your system of equations, so this is the same system I wrote in general, and you solve for your unknowns. So on the first equation, you're just going to solve it for x1. So I'm just going back to this equation here that I wrote in green, and I'm taking that first equation, and I'm just solving it for x1. And then I'm going to take the second equation, I'm going to solve for x2. And I'm going to take the third equation and I'm going to solve for x3. So the idea is that as long as you guess an x1 and an x2 and an x3, you can iterate on that guess by plugging all those into the right-hand side and replacing them on the left-hand side. And you can continue to do that as many times as it takes until they stop changing. And once they stop changing, you can assume that those are the solution. So the second step is to repeat that calculation until x1, x2, and x3 stop changing. So if you're repeating something until, what kind of loop is that? That's a while loop, right? So you just basically throw those 3 lines into a while loop, and you want to create this condition. It's called a residual. It's used in any modeling code that you'll ever use. You'll see the word residual all over the place. And a residual is just taking whatever it is you're iterating on, subtracting it off of what it just was the previous iteration, and stopping once that subtraction is small. And you always do the absolute value because you don't care how close it is in either direction. You just want it to be close. And we use this term epsilon. A lot of times in MATLAB, I'll use the variable name EPS. I think that's an intrinsic function now, but you can override it. And it's just a small number. So one thing that often confuses people in programming is that you can't set it, you can't wait till it's 0. That's impossible. It will never be 0. So you just want it to be small. 10 to the minus 3 is not that small. You can make it smaller, 10 to the minus 8. Precision of the machine is like 10 to the minus 30. So you could go there. It might just take a lot longer. But you just want it to be small enough. And that's an opinion that you get to make, how small it needs to be. So new and old are just the latest and the previous iterations. So this algorithm is pretty straightforward to write. The last algorithm is an elimination method. And it's not that different from an inverse method, except for it takes away some of the computations. And so like, just to give you a cost breakdown, this method takes 2n cubed over 3 flops. A flop is a floating point operation, so it's any multiplication, division, addition, subtraction. So it takes that many flops where n is the number of equations. And inverting a matrix takes 4n cubed over 3 flops. So it's like twice as fast, twice as less. So it's not great, but it's better. And the method that I'm going to have you program is the Gauss elimination method. Gauss named everything after himself. And the way the Gauss elimination method works, and I don't know why no one has seen this kind of thing before. Like, I did this all the time. Maybe I was doing this by choice. I don't know. But I don't know if it was because I was a tutor in math, but we had to do this all the time, this method. But it's basically taking your A matrix and augmenting it, which just means putting it next to the B matrix. And then you do a series of row reduction and backward substitution. And have you guys heard of this before, row reduction and backward substitution? Or this is English, it's math. This algorithm is a little bit trickier to write, so I'll probably be helping you guys a little bit with this one. But the basic idea is you row reduce and then you backward substitute. So the first step is called elimination. And you want to get this matrix to look like this. You want to zero out 2 unknowns from your last equation and 1 unknown from your second equation. I'm putting primes here because these ones that I'm putting primes on have gotten operated on. So if there's 1 prime, they got operated on once. If they have 2, they got operated on twice. But the basic idea is you want to reduce the array so that these are all 0. And then you can see that it's pretty straightforward then to back substitute. So this unknown, the third unknown, can easily be solved for because these are 0. So here you have A33 times x3 equals b3. So you can easily find x3. And then you'll just go backwards and find x2, and then go backwards and find x1. So the first step is to eliminate those 3 unknowns. And then the second step is to back substitute. So for example, x3 would just equal b3 double prime over a3 double prime using that augmented row reduced. And then x2 is going to equal b2 prime minus a3 2 prime times x3 over a2 2 prime. And then keep in mind you already know what x3 is because you found it in the previous step. And then x1 can be calculated using just solving for x1 now, because now you know everything else. And you'll notice that the first equation in Gauss elimination never gets touched. So the basic idea is an inverse method, as opposed to this, it would actually convert this into an inverse. So this 3 by 3 would be an identity. It would be 1, 1, 1 on the diagonal. So that would be a lot more operations, basically, than this process. Just about twice as many operations, basically. But this method, the elimination method, is exactly how you've probably always solved system of equations. So if you have 2 equations and 2 unknowns, what do? You eliminate one of the unknowns, solve for it, and then back substitute in to get the other one. So you're doing that here, just in general, and for any number of equations, any unknowns, and it's just way more difficult than that, but you can do it. So give it your best shot, think about it before you come into lab, and then we'll help you through this a little bit once you get into lab. But the iterative method is very straightforward, and you should be able to do that completely on your own.